Hey guys, in this video we're going to have a look at traveling waves. First we're going to look at the types of traveling waves. We're then going to look at their anatomy and finally their equation. Right, so let's have a look at some diagrams. Alright, the first type of wave is called a transverse wave. So if you imagine you sort of flick a string at this end, you'll send a pulse down in this direction and it will move along the string like that. What makes this wave transverse is that while the wave is traveling in this direction, the motion of the string or the particles is in this direction, perpendicular to the motion of the wave. That's what makes it transverse. The next wave we're going to look at is a longitudinal wave. Right, so if you imagine you sort of pull a spring or compress a spring this way, the compression will sort of move down, propagate down the spring in that direction. So what makes this one longitudinal is that while the wave is traveling this way, the direction of the particles or the direction of the movement of the spring is in the same direction, parallel, right? So that's what makes a wave longitudinal, that the direction of the particles is parallel to the direction of the wave. Now there are other types which involve a combination of these two we've discussed, but they're not really included in this course. So let's move on to the anatomy. Right, here we've got a sine wave. A sine traveling wave can be set up by a wave generator, quite a common one you'll see in this course. And basically what we need to know are these two things. A is our amplitude, and it's how far a particle will deviate from its equilibrium point. And we've seen that before, so I won't go into too much detail with that. But what this distance here is the place from peak to peak, right? That is known as our wavelength. And it is given the letter lambda, or the symbol lambda, and it's basically the distance on a wave that it takes for a particle to move from one spot and return back to that same spot. So it can be the distance from peak to peak, it can be the distance from here to here, it can be the distance from trough to trough, it doesn't really matter. All those are the same distance and they are called a wavelength. And those are the two pieces of anatomy that we know, or we need to know for this course. Right, we're now going to look at the equation of a wave. And that's straight off the formula sheet. Y equals a sine kx minus omega t plus phi. Now what you'll notice is that y is actually a function of two different variables, x and t. So that means at a different point along the wave, at different times, different combinations of x and t will give you different heights. And if you think about a wave, that seems to make sense. So I suggest you do some practice questions and to try and conceptualize that idea of an equation with two variables. With k and omega, k is equal to 2 pi on lambda, so 2 pi divided by the wavelength, and it's called the wave number. Omega, like we saw in our oscillations, is still equal to 2 pi times the frequency, and both of these are on your formula sheet, and omega is still called the angular frequency for a traveling wave. Right. And if you substitute those in to that above formula, we end up with something that looks like this. Y equals a sine 2 pi on lambda x minus 2 pi ft plus phi. So you can see why we've given k and omega as those substitutions, because it makes it easier to write, and also it can help us answer some questions. But first we're going to look at a relatively simple example written down here. Given the wave equation below, find the wavelength, frequency, and vertical position of the wave at x equals 0.2 and t equals 1 second. So there's our equation, y equals 0.26 pi t minus 4 pi x plus pi on 3. Now what you need to first notice here is that the omega and the k have been swapped around, the x and the t have been swapped around, so you can't let that fool you. So first we're going to start with our omega. Omega is always next to the t, so our omega is 6 pi here. So even though it's in a different order, we can still answer it. We know that omega is actually equal to 2 pi f from our formula sheet. Right? Divide both sides by 2 pi, we end up with f equals 3 hertz. Quite simply. Next, we'll look at k. K is always next to the x. Right? K equals 4 pi. We know that k off our formula sheet is equal to 2 pi over our wavelength. And with a little bit of rearranging, we end up with k equals 1 over 2 meters. So our wavelength for that wave is 1 over 2 meters. Right, finally, we need to find the position of the wave at these variables. So what we need is y at 0.2, 1. So that's x and t. And that'll give us the following if we just substitute those values in. Right, put that all in your calculator and you find that the vertical height or vertical position is minus 0.1989. Now we know, just to talk about what that answer means, that's pretty close to our 0.2, which we know from previous videos. That's actually the amplitude of the wave, seeing as the maximum value of sine anything is 1 or minus 1. So at the point 0.2 along the x-axis, and after 1 second, we end up with our vertical height being almost the maximum height of y, but below the axis because of that negative sign. And that's how we use that wave equation, and that concludes this video. Thanks, guys.